All right, folks, this is Josh Price. I felt like today's lecture on November 13th, I felt like I didn't do a very good job of communicating what I had intended to do. So I'm going to record a new version of that lecture. I will post it on Learning Suite and on YouTube and make the notes available to you. Hopefully between what I do now and what we did previously, I can get the point across. If you want to access the original recording, you can go to the online tab of Learning Suite and select the Zoom recording for November 13th. All right. So last time on Wednesday when we were talking, we were talking about secondary kinetic isotope effects, which typically involve rehybridization of carbons. And the place where we're investigating the isotope effect is doing proton versus deuterium at the carbon that's being rehybridized. The origin of this kinetic isotope effect is in differences in the strength of a particular vibrational mode for sp2 versus sp2 hybridized carbons. Here is an sp3 hybridized carbon. These straight lines are in the plane of the page. The wedge is coming out at you. The dash is going back into the page. This carbon-hydrogen bond is wagging forward, bending forward out of the page, and then bending backwards into the page. We call this an out-of-plane bend. And again, you have to think of that hydrogen is moving out towards you and then back away from you. It has this vibrational frequency expressed in wave number. Of course, you can convert that into hertz if you want to. But for the sp2 hybridized carbon, it turns out that same out-of-plane bend vibrational mode, again, proton coming up out at you from the page or going back into the page, has a much lower frequency, meaning it has a weaker or looser force constant. And the reason for that is there's less steric hindrance about an sp2 hybridized carbon. There are methyl groups to sort of bump into for the out-of-plane bend on the sp3 carbon, but not as many things to bump into for the out-of-plane bend on the sp2 carbon. So in changing hybridization from sp3 to sp2, we're changing a force constant from stronger to weaker. Now, remember what we talked about last time. The 0-point energy difference that you're going to see is proportional to the strength of the force constant. So if we go from a stronger force constant to a weaker force constant, that means that we're going from a larger 0-point energy difference to a smaller 0-point energy difference. And this will create a situation in which we can get a kinetic isotope effect. So here's an energy diagram. Again, don't worry about copying it down in your notes. It'll be the notes will be posted to Learning Suite. We're showing a generic reaction coordinate diagram where we're moving from an sp3 hybridized carbon-hydrogen bond to an sp2 hybridized carbon-hydrogen bond through a transition state. We're taking a cross-section of the vibrational modes available at in the starting material for this carbon-hydrogen bond. Here's that vibrational energy well. Here is a carbon-deuterium bond. Here is a carbon-hydrogen bond. Carbon-deuterium has a lower 0-point energy due to its larger mass. The 0-point energy difference we observe for this sp3 hybridized carbon is sizable. In contrast, over here for the sp2 hybridized product, here's the vibrational energy level. And because the force constant is weaker, that delta ZPE is smaller. And so there's less of a difference between carbon-hydrogen versus carbon-deuterium. The transition state is somewhere between those two extremes, but if there's substantial sp2 character on that carbon in the transition state, we can expect this 0-point energy difference in the transition state to be less than the 0-point energy difference in the starting materials. And that's just expressed here. So 0-point energy for the difference for sp2 should be smaller than in the transition state, which should be smaller in the sp3 hybridized starting material. So if the 0-point energy difference is smaller in the transition state than in the starting material, that's the same thing as saying that the energy to get from the ground state of the carbon-deuterium bond in the starting material to the ground state of the deuterium bond in the transition state is larger than making the same jump for the carbon-hydrogen bond. That tells you that deuterium is slower than hydrogen in this rehybridization reaction. And for these kinds of kinetic isotope effects, we expect something in the range of 1 to 1.4 or greater than 1 for going from sp3 to sp2. And we call that a normal secondary kinetic isotope effect. Now, if you were going the other way from sp2 back to sp3, you would expect to go from a smaller 0-point energy difference to a larger 0-point energy difference. And that would result in an inverse kinetic isotope effect where the ratio of rate constant for hydrogen versus deuterium is less than 1. All right. When might that be useful? Well, you can use this understanding and use secondary kinetic isotope effects to rule out potential alternative reaction mechanisms that you're studying. The one we'll talk about is the mechanism of D-amino acid oxidase and its oxidation of an amino acid to an amino acid using the cofactor FAD, flavin adenine dinucleotide. So in this reaction, an amino acid loses its proton, and you get to this amino acid enolate. And from that point, there are sort of two mechanistic possibilities. The first, which we'll call path A, is a 2-electron pathway. You have the alpha carbon of your enolate attack one of the nitrogens of FAD in a typical nucleophile attacks electrophile fashion. There's places for the electron to go because of this extended conjugated system, and you create a new carbon-nitrogen bond, and you have to move pi bond over here, and this pi bond out as lone pairs on the nitrogen. After you get there, there are several subsequent steps that allow you to get to the fully reduced form of FAD, which is called FADH2, and then this oxidized amino acid, where instead of having an alpha carbon that's bonded to 4 different things, you have an alpha carbon that's bonded to only 2 or 3 different things. A key feature of this proposed 2-electron mechanism is a change in hybridization. So enolates, that is alpha carbon, negatively charged alpha carbons adjacent to carbonyls, are generally sp2 hybridized. Whereas after the reaction, that alpha carbon is now bonded to 4 things and would be sp3 hybridized. So if this were the mechanism, if the 2-electron mechanism or path A were the correct mechanism, we would expect to be going from an sp2 carbon to an sp3 carbon. That's going from something with a weak force constant to a strong force constant, or in other words, a small delta ZPE to a larger delta ZPE. So that's a situation where we can expect an inverse secondary kinetic isotope effect. That is where the rate constant for the reaction with proton versus deuterium will be less than 1. Let's look at the alternative hypothesis, and that is that you again have an enolate. Again, the alpha carbon of the enolate is sp2 hybridized, but instead of attacking the nitrogen of FADH2, instead we do a single electron transfer, and we'll call that path B. SET stands for single electron transfer. It's hard to draw the mechanism of this. It's like you take your hand and you pop an electron out of your enolate and put it into the pi system of FAD. The products are these two radicals. This is the FAD radical anion. Here is your extra electron. We've had to rearrange the pi bonds to accommodate that extra electron. But if you count them all up, you can see that we've only gained one radical anion here. And then, of course, because we've removed the electron from the alpha carbon, now we only have one electron on that alpha carbon. Now let's look at the hybridization difference at that alpha carbon before and after the reaction. Amino acid enolates are sp2 hybridized at the alpha carbon. That's what we said here. Same thing here. Radical species, though, continue to be about sp2 hybridized. And so there's not a big change in hybridization. And so we would expect to see no kinetic isotope effect or rate constant with proton versus rate constant with deuterium equals 1. Now, it's sort of difficult to do the deuterium experiment, hydrogen deuterium experiment with amino acids, because in the reaction mechanism, you first got to remove a proton and then you would need this R group to be a deuterium. And that can be somewhat tricky. You worry about scrambling of where the deuterium is. So instead, the researchers who did this study, and you can look up the reference, it's in your text, used this unusual substrate analog. You've got a nitro group doubly bonded to a carbon. And if you look, a resonance structure for this nitro compound would have an sp, it looks kind of like an enolate, right? It would be sort of an sp2 hybridized carbon that is nucleophilic or bears part of the negative charge. And that substrate analog is nice because it's already an enolate to begin with, so you can use it as starting material in your reaction without having to worry about the first deprotonation step. And we can incorporate deuterium versus hydrogen in this molecule. So again, let me show you what the two possible pathways are. Here's blue pathway A, a 2-electron step. Basically, the sp2 hybridized alpha carbon is going to attack the nitrogen, and the intermediate after that is going to have an alpha carbon that is sp3 hybridized. So again, sp2 to sp3, we expect to see an inverse secondary kinetic isotope effect. In contrast, if the radical mechanism is operative, you go from an sp2 carbon to still an sp2 carbon. So if the single electron transfer mechanism were operative, we would expect to see no kinetic isotope effect. And in fact, what we observe is a inverse secondary kinetic isotope effect. In other words, path A is the operative one because we see that Kh over Kd is less than 1. So that's a case, that's where kinetic data, like an example of where kinetic data have allowed us to rule out a potential alternative explanation. If you want to learn more or see the original paper that did this work, it's in JACS in 1997, and that is the year I graduated from high school. And let's see, volume 119 and page 1155. So go ahead and look that up, and if you want to know more, you can investigate the references therein. Okay. So in the remainder of our time today, I want to talk about a method for keeping track of protons in reaction mechanisms. So we're going to use something called HD exchange with solvent. And we're going to use kinetics. And we'll do all of these things with the goal of keeping track of how many protons are in flight or participating or moving in the rate determining step of a reaction. This is going to require a little bit of setup, and there's a little bit of math. And I'm afraid I didn't explain it that well to you when I was in class earlier today. I'm afraid I won't do a very good job now, but we're going to try to get through it. So imagine a molecule where you have a proton attached to a heteroatom. And then imagine a solvent, which we're just going to represent with S, that is deuterated. And imagine that these are exchangeable via hydrogen bonding. And this is absolutely something that you're probably already familiar with. For example, if you have a molecule with an alcohol and you do an NMR experiment in D2O, you don't see the proton on the alcohol because it's been replaced by deuterium. So it's that kind of exchange reaction we're thinking about. This is a exchangeable site in a molecule that we're interested in, and this is an exchangeable site in our deuterated solvent. And that's going to be in equilibrium with the now deuterated starting material, or deuterated exchanged site in our molecule, plus our solvent that now has hydrogen on it. And we can write an equilibrium for this exchange process, equilibrium constant for the exchange process. It should be the concentration of our exchanged molecule times the concentration of proteated solvent divided by the concentration of our unexchanged molecule times the concentration of our deuterated solvent. All right. And then if we want to play a few rearrangement games, just a little bit of algebra, we can actually represent this in a way that qualitatively makes a little bit more sense. This equilibrium constant for exchange basically tells you how much deuterium prefers to be attached to whatever the group is in our molecule versus how much it prefers to be attached to solvent. And I will point out that in our experiment, the solvent concentration is way, way, way higher than the concentration of our molecule, such that you can expect this number here to be roughly constant. All right. And we're going to, because this equilibrium constant exchange tells us how much deuterium prefers to be attached at the site in our molecule versus how much deuterium prefers to be in the solvent, we're going to call this exchange constant phi, Greek letter phi, and we're going to call that a fractionation factor. But remember that the fractionation factor tells you how much deuterium prefers X versus S relative to how much H prefers X versus S. Okay. And you can measure numbers for various kinds of OH bonds and measure their fractionation factors. However, that's not really what we're going for here. We want to develop the mathematical and experimental tools to be able to follow how many protons are participating in the rate determining step. So I'm going to make the situation a little bit more complicated. Let's imagine what the interplay is between an actual reaction and HD exchange. All right. So suppose you have a reaction in which reactant 1 that's attached to a proton reacts with reactant 2 that's attached to a proton. Both of those protons are exchangeable, and you get product 1 attached to a proton and product 2 attached to a proton. So that's the proteated reaction, which would have the following equilibrium constant, P1H times P2H divided by R1H times R2H. And we could write a similar set of expressions for the deuterated reaction, where we have R1, a site in molecule 1 attached to deuterium, a site in molecule 2 attached to deuterium. We get product 1 with deuterium and product 2 with deuterium. And we could measure the equilibrium constant in deuterium, which would be exactly analogous to what we drew above for the proteated reaction, only now we've got deuterium. Now imagine you do this experiment and you measure these two equilibrium constants, and then both in the proteated case and in the deuterated case. So what? What does that tell you? And it turns out we can get some more information from the system if we use the following mathematical manipulations. And first, we're going to imagine doing reaction 1, the proteated reaction, and reaction 2, the deuterated reaction, all at the same time. And we're going to imagine that we're doing this in a mix of solvent, proteated solvent and deuterated solvent, where the ratio of SD over SH is constant. Okay. And let's just say that we want to know and we can measure the equilibria in the presence of just protons versus just deuterium. That equilibrium constant is equal to that ratio divided by this for the proteated case. Alternatively, if I want, I can make this the ratio of the deuterated equilibrium constant versus the proteated one. We're choosing that for a reason that you will hopefully see in a little bit. Okay. Here is the ratio now based on these equilibrium expressions. Here's the ratio of the equilibrium constant for the deuterated molecules versus the equilibrium constant for the proteated molecules. And now we're going to do a little bit of rearranging that hopefully won't bother you that much, but is going to be useful to us in a little bit. These two numbers are here. These numbers are in the denominator. I'm just moving where they are. Hopefully you can convince yourself that what I'm showing you here is true based on what you know about multiplication and division. All right. Now, with that rearrangement in place, we're actually going to do something that at first is going to seem unusual. We're going to multiply this fraction, this ratio, by the concentration of proteated solvent divided by the concentration of deuterated solvent. To keep this expression true, though, what we do to the denominator, we have to do to what we do to the numerator, we have to do to the denominator. And then, for reasons that should become clear in just a moment, we're going to do that again. At first, this looks like pointless algebra, but it's designed to show you the connection between observed equilibrium constants and the preference of each site in this molecule for hydrogen versus deuterium. So now, with a little bit of commutative property of multiplication, we're going to just change things around. Excuse me, sorry about the cough. And then we'll do the same thing here. Okay, and all of that is equal to the ratio of our equilibrium constant in deuterium versus our equilibrium constant in hydrogen. Now, these expressions in parentheses ought to look somewhat familiar to you. What do they look like? Well, they kind of ought to look like this exchange constant or fractionation factor. Each of these numbers in parentheses tells you how much deuterium prefers to be on the molecule product 1 versus being on the solvent. And so we're going to actually write our equilibrium expression in a new way. We're going to use phi 1 with a P for our product, for product 1. So this is the fractionation factor for deuterium versus hydrogen at a site in product 1. Similarly, this is going to be the fractionation factor for deuterium versus hydrogen at the site in product 2. And then we're going to do the same thing in the denominator, only it's for reactants. Okay? So what this tells you is the equilibrium constant for a reaction, how much better deuterium is than hydrogen, or rather how the difference in the ratio between equilibrium constants for the reaction done in deuterium versus in hydrogen is related to how much deuterium prefers site 1 in product 1, site in product 1 versus solvent, times how much it prefers the site in product 2 versus solvent, and divided by, and then the same thing for starting materials 1 and 2. So if you can measure the preference for hydrogen versus deuterium at all of these sites, you actually can calculate what the ratio of relative equilibrium constants are. Now, this is true for an arbitrary number of sites in one or many molecules that are reacting. And so to generalize, we're going to use the symbol pi. The symbol pi it means the product of a bunch of stuff, just like the symbol sigma means the sum of a bunch of stuff. So the product of all the individual fractionation factors for products divided by the product of all the individual fractionation factors for reactants. Hang on, it's going to get a little bit worse before it gets better. It turns out that we can do the same thing with rate constants, only this time the thing in the numerator is going to represent the product of the fractionation factors for all of the sites in the transition state divided by the fractionation factor for product of the fractionation factors of all the sites in the starting materials. Okay, so we've developed some mathematical tools. Now we're going to set up a situation where you'll be able to see how we can do an experiment and determine just how many protons are in motion. Okay, and this strategy is called Proton Inventory. All right. So imagine that we're going to do a reaction of, imagine we're going to do a reaction in a mixture of deuterated solvent versus proteated solvent. Okay, and we're going to define N as the mole fraction of deuterium, or in other words, N equals SD divided by SD plus SH. All right. Then the rate constant that we measure for of our reaction, so Kn is the rate of a reaction in N% mix of deuterated solvent plus 1 minus N% proteated solvent. And that rate we're going to assume is the weighted average of the rate of the proteated reaction times how much protonated solvent we have versus deuterated solvent, plus the rate constant, intrinsic rate constant for the deuterated reaction times the fraction of deuterium that we have. All right, so this expression is a weighted average. It just says that the observed rate constant should be the weighted average of the deuterium rate constant and the proteated rate constant, weighted according to how much deuterium is there versus protons. When N equals 1, Kn equals Kd. When N equals 0, Kn equals Kh, right? Okay. We're going to now define a kinetic fractionation factor. Your book does not make clear how this number is related to the fractionation factors we've described above. I'm going to give it the capital Greek letter phi. And I apologize for that confusion. I need to learn more. But we're going to define that kinetic fractionation factor as the ratio of the intrinsic rate for deuterium over the intrinsic rate for the proton. And we can rearrange that to say that fraction capital letter phi times the rate constant for the proteated reaction is equal to the rate constant for the deuterated reaction. Then we can convert our expression for the rate constant in a mixture of hydrogen and deuterium to the following expression. And we can factor out the KH. And then we have 1 minus n plus capital phi times n, where n is the mole fraction of how much deuterium we have. And then I can divide Kn by Kh, and that gives me 1 minus, let's see, 1 plus capital phi minus 1 times n. All right. And what we have just said is true based on this fractionation factor. This equation is true for one proton exchange site. And this expression makes sense. If n equals 0, then Kn equals Kh. If n equals, then Kn equals phi Kh or Kd. So now we're going to go back to our expression of Kd over Kh as being the product of these individual fractionation factors. And based on our analysis here, we're going to rewrite our equation Kn over Kh as equal to the product of 1 plus capital phi minus 1 times n, where this is for site I in the transition state, versus the product of 1 plus capital phi in the starting material for site J times n, where again n is the fraction of solvent versus solvent that is deuterated versus proteated. The derivation here, and let me tell you, the jump from here to here is unclear to me. And so there's a little bit more reading that I want to do. And so this, if we measure a reaction rate in a mixture of deuterium and proton versus a reaction rate with just proton, it's going to be influenced by all the sites where the fractionation factor does not equal 1. And when does the fractionation factor not equal 1? When there is a preference for deuterium versus proton at a site in a transition state. We're going to make the assumption that only phi equals 1, phi does not equal 1, only in the transition state, phi does not equal 1 only if the HX bond is somehow participating or breaking in the transition state. And we're also going to assume that the fractionation factor in our starting material, our reactants, are basically equal to 1. And this is the same as saying that bond strengths of XH versus SH and XD versus SD are similar, which is a reasonable assumption for a lot of the XH types of bonds that are present in biomolecules. All right, so let's look at how this equation would look if we only have one site. If we make the assumption that all of the fractionation factors in the reactants are equal to 1, this whole denominator goes to 1. So based on that assumption, our equation simplifies a lot to equal the product of 1 plus fractionation factor for site I in the transition state minus 1 times N, where N is the composition of our solvent. If we have only one site, then Kn divided by Kh is equal to 1 plus fractionation factor for site 1 minus 1 times N, and a plot of Kn divided by Kh versus N will be linear. In contrast, if we have two sites that are involved, two protons that are involved in the reaction, the ratio in our mixture versus in with just pure protons will be 1 plus fractionation factor of site 1 in the transition state minus 1 times N times 1 plus fractionation factor of site 2 in the transition state minus 1 times N. And so you should be able to see that a plot of Kn over Kh versus N would be quadratic, because you're going to have N squared over here, right? And so this is a way you can use to determine whether there's one proton involved in the reaction, rate determining step of the reaction, versus two, and it's called a proton inventory. And you simply do the reaction in a solvent that is purely proteated versus mixtures of the proteated and deuterated solvent. And then you plot the ratio of rates versus the composition of the solvent, and you see if it's linear, quadratic, or cubic, and that can tell you how many protons are in flight in the rate determining transition state. So here's an example. We didn't quite get to it in today's lecture, and I will talk about it at the beginning of next class. But here's an example of a reaction catalyzed by ribonuclease. It's the hydrolysis of a cyclic phosphodiester. And the hypothesized mechanism is that an imidazole removes a proton from water so that hydroxide can attack the phosphorus, breaking the diester. The oxygen that leaves picks up a proton from this protonated imidazole. And the proposal is that all of that is happening in the same rate determining step. An alternative proposal would maybe be that first this deprotonation happens, you get an intermediate, then the attack happens and you get an intermediate, and then the protonation of that leaving group happens. But it's interesting to know whether it happens in separate steps or all at once. And this is a question, a perennial question that is troublesome for people that take biochemistry or that take 352 and learn some biological reaction mechanisms. How do you know when a proton transfer occurs in the same step versus a different step? And the answer is you do a proton inventory. So the folks who did this experiment measured the ratio. This is basically on this axis Kn divided by Kh. That's the rate constant in mixtures of deuterium and water, D2O and water, versus the reaction in just water. And in black dots here, you have the plot of Kn over Kh versus the amount of D2O that's present, the mole fraction of D2O that's present. The dotted line represents what you would expect for a linear relationship. And instead, you see that there's some curvature. So if you fit the data, this is a quadratic relationship. And in fact, this is the square root, the open circles are the square root of Kn over Kh, which show you that that versus n is linear. And so this is clear and convincing evidence. You've got a quadratic relationship. That means two protons are in flight during the reaction. And that is a complicated but very powerful technique. If you want to learn more about it, you should go look at the following reference. This is in JAX in 1986. I was 7 years old in 1986, volume 108, 53, page 5316. All right, so that concludes today's second attempt at the lecture. Hope everything works out for you, and I hope you have a good weekend. Bye-bye.